In the last segment, we started deliberately dragging data away from the center. We started looking at distributions that have long tails on one direction or another. And in this segment, we're going to try and get a handle on just how big those tails can be. How far can you be from average? So we'll start with a specific question. I've got a group of people, and on average they're 20 years old, and the question is, what proportion are more than 80? Now, any way you look at it, surely your answer is going to be not a whole lot. There aren't too many people aged over 80 in the first place, and this group seems young. On average they're 20 years old. So every instinct is saying that the answer isn't going to be large. But instincts are also saying that we can't get an exact answer. We don't know anything about this group other than its average. So we're not going to be able to say exactly what the proportion is, and I don't think you've got enough even to get a decent approximation. So what do you do? Do you just stick with not a lot? Nope. You give thanks to a wonderful, wonderful Russian mathematician called Andrei Markov. There's a whole family of random processes named after him, Markov chains, and they form the basis of much of probability and statistics, greatly in current use. Markov came up with a simple bound on this proportion. So a bound is not an answer, it's not an approximation. It's a boundary. He says this proportion can be no more than a certain number I'm just about to tell you. But before I do that, for all you Canadians out there, I'm well aware that there's an ice hockey player called Andrei Markov, currently playing different guy, really, different guy. So before we get to Markov's bound, I need to warn you. You are about to see one of my wonky hand-drawn pictures because you are now expert at looking at distributions. And so the diagrams are going to get rougher and rougher because you don't need all the detail. You can deal with this. I told you it was wonky. So here's a distribution of ages. I don't actually know what the shape of the distribution is. I've just drawn something. What I do know is that ages cannot be negative. So I'm starting at 0. And the average was given to us as 20. And so I've drawn something that looks roughly like a balance point at 20. Yeah, it's kind of okay as a balance point. Maybe it should have been a bit more to the right. But the question was about the proportion that are over 80. So 80 is a good number to get at. And if this distance is 20, then that's 20 kind of another 20 and another 20. I have 4 20s. And I am looking at the proportion above 80, and proportions in histograms are areas because proportions are equivalent to percents. And so this question is about the shaded area. What percent are in this shaded area, or what proportion are in that shaded area? And that's what Markov tried to get a handle on. And what he did was he said, I'm going to look at a distribution that is non-negative, so 0 or more. And if you think about it, I think every single one of our distributions thus far has been non-negative. It is certainly the most common kind. So you look at a distribution that is non-negative and you walk some number of averages out. So there's an average and there's one more average, and the way I've drawn it, I've walked another 1 and a bit averages out. And we're going to call that k times the average. What is k? K is however many averages you are at here. So here k is 4 in our old example. The average was 20, we're starting at 80, that's 4 averages. So supposing you start at k averages, then Markov did a little calculation that says that this tail, the percent in this shaded region, is at most 1 over k. Simple little answer which says that in your distribution of ages, average 20, the proportion that are in the shaded region over 80 is at most 1 in 4, at most 25%. And so keep that picture in your mind. What we'll do next is we will state it formally and we will look at it carefully and see what the bound does and what it doesn't do. It's called a tail bound because it is a bound. It gives you some sense of limits on the tail of a distribution. Probability and statistics are full of tail bounds because we are very, very interested in how far off you can be from the center of the distribution. Because the center is kind of where we expect you to be, but we know that you can be quite far away. And so tail bounds give us some sense of how far off you can be. To state the inequality formally, k is any positive number, and the inequality says, if your list has only non-negative entries, it is very important that you're blocked at 0, you cannot go below that. Then the proportion of entries that are at least as large as k times the average is at most 1 over k, and that is the picture that we had before in English. And just to go through a bit more English, at least as large as is the same thing as greater than or equal to. So the proportion of entries that are greater than or equal to k times the average. That's what I'm looking at. Greater than or equal to, you'll remember, has that symbol. That proportion is at most 1 over k. At most means that's the biggest it can be. It can be no more than 1 over k. And so if I take a specific example, if you take a list of non-negative numbers, then the proportion that are at least as large as 4 times the average is at most a quarter, that is no more than 25%. If you look at the proportion that are at least as large as 10 times the average, then that proportion is no more than 1 in 10. And just to be sure that we know what this is saying, it's important to be clear that this is a bound. It is not an answer. It's not saying that the proportion is 110. It's not saying it's approximately 110. It's not saying that we're guessing that it's 1 in 10. 1 in 10 is a bound. So the proportion could be exactly 1 in 10. It could be quite a bit less than 1 in 10. It could even be 0. But what the bound is saying is that the proportion cannot be more than 1 in 10. No way, no how. If you draw any non-negative distribution whatsoever, and you put down the average, and you put down the point that's 10 times as large as the average, then the tail beyond that cannot be more than 1 in 10, no matter what shape you've drawn. Now, I haven't proved this by any means. I might upload a PDF that has the algebra proof of it. The algebra is not so hard, but I haven't required that level of algebra in this course, so I'm not planning to do it in the lectures. What I'd like to do is I would like to look a little more carefully at the question that we started with, which was that the average age of a group of people is 20 years. What proportion are more than 80 years old? And I'd like to put it together with the inequality that we have carefully. So our question is, what proportion are more than 80 years old? And we know we can't answer that. We can't answer exactly what that proportion is, or even approximately. But Markov gives us something. Markov says, as 80 is 4 times the average, we are looking at the proportion that is more than 4 times the average, and so the proportion beyond 4 times the average, according to Markov, is at most a quarter. We've said this a few times now, so why is it in quotes? It's in quotes because it's a little loose at the moment. In the question, the proportion we're looking at is the proportion who are more than 80 years old, strictly greater than 80, whereas the proportion that Markov addresses is the proportion that are greater than or equal to 80 years old, greater than or equal to. So is this at most 1/4 still correct? It is. It's a bound. It is not an answer. And so let's just see which of these two groups is bigger. I believe this second group, greater than or equal to, is bigger. Because one way to form the more than 80 group, those are the people you're interested in, you can form them by gathering together everybody who is 80 years old or older and then being very rude. At that point you say, excuse me, if you're 80, could you please just go away? And once they've gone away, you are left with exactly those who are more than 80 years old. So the set in the question cannot be bigger than the set that Markov is dealing with in his inequality. And so the proportion that are more than 80 years old is at most the proportion that are greater than or equal to 80 years old. And that has been dealt with by Markov's inequality, and that we know is at most 1/4. So if the bigger thing is at most 1/4, then certainly the smaller thing is at most 1/4 as well. And so you don't really have to worry about whether the endpoint is included or not included. The bound works in both cases. And finally, I'm going to take care of an issue that I'm sure is bothering some of you, and that is the question like this. What proportion are at least as large as half the average? So Markov said, I'll look at the proportion beyond k times the average. So now k is a half. And so the inequality says the proportion is at most, it was 1/k. So 1 divided by a half, which is 2. That's a proportion that is 2. In other words, it's 200%. Huh? Well now, let's not panic. This is not a problem. Markov isn't wrong. What's going on is that you've got a proportion and you're saying that it is at most 200%. That is absolutely true. That's true of every single proportion in the world. Every proportion is at most 200%, since in fact every proportion is at most 100%. You don't need a famous mathematician to tell you that a proportion is going to be at most 200%. So what just happened here? What happened here is that Markov's inequality is still correct for k, a fraction, but it's just not useful. We knew already that this proportion can be no more than 200%. So just to take one more look at this, this is the fight between logic and practical significance. So if somebody comes and tells me that I have at most 3 heads, they're a very strange person. But aside from that, they are logically completely correct. I do have at most 3 heads. I have 1 head, and that is not more than 3 heads. So yes, I do have at most 3 heads, and I really don't want to think about that. But it happens to be true. And that's the situation we're in here. We've got a proportion, and we're saying it's at most something huge. That happens with bounds. So should we throw it out? No, we should not throw it out. We should just not use it for small k. The bound is for the tail that is far away from the average. And remember, you're blocked at 0, so you're looking at very large k. 10 times the average, 20 times the average, there the bound starts to be useful. Markov's bound is most useful when k is large. That's when you're looking at entries very far above average. And, very far is a semantics, but at least a couple of averages on out. That's when you should be using the bound.